Okay, today we're going to be solving the Schrodinger equation for the harmonic oscillator. As you guys probably already know, the Schrodinger equation comes in the form of H psi equals E psi, where H is the Hamiltonian and E equals energy. If we split this down further, we find that H as an operator equals the kinetic energy operator plus the potential energy operator. And basically to find the solution to the Schrodinger equation, we want to find out what the kinetic energy operator and the potential energy operator are in the first place. So if we rewind back to basics, we look at a spring attached to a mass, right? And the spring with a mass on it goes up and down and up and down and up and down. So the displacement and the distance it goes up and down is going to be called x, and the force opposing it, F, is basically called the restoring force and is given the equation F equals minus kx. And it's F is also, I'm going to label that as a restoring force. And it's also proportional to the displacement from equilibrium. And that's an important thing to remember. Okay, so we're trying to find out what the potential energy is. So we know that F also equals minus the gradient of the potential energy. So we have this equation right here. And what we basically need to do is that we need to rearrange this equation. So if we bring dx across to this side, we have f dx equals minus dv. And we want to find out what the potential energy is, so we have to integrate both sides. And at the same time, we also know that f equals minus kx. So if we plug that in, then we have minus kx dx equals the integral of minus dv. And now we just go ahead and integrate, which is pretty simple. We can cancel the minus signs, so we've got kx squared over 2 equals v. And that is our potential energy. This is a really important part, and we're going to keep that in a box. So I'm going to rub all this off. And I'm going to put it here. V equals kx squared over 2 alongside which is also very important. Okay, now the second part of what we need to do is that we need to find out what the kinetic energy operator is. And the kinetic energy operator is T equals a half mv squared. And we could also rewrite a half mv squared as mv squared over 2m, because when you multiply out this, then you end up with m squared v squared over 2m, and then the m's cancel and you end up with the same as you already had before. And also, we also know that we have to find out what the momentum is, and the momentum. Well, we have to find. I'm basically going to do some definitions now. An observable is a measurable property like a bond length, which is represented by an operator B. And all operators are built from operators of position and momentum. So the operator in position x is B equals x hat. Okay, so for momentum in x, then we have B equals px equals mvx, which is mass times velocity. and it also equals minus I h bar d by dx. And these are just things that you need to remember. And now we know that we know this equation and we know this equation, so we find out that mv here is the same as the mv here. So if we plug the value, because mv equals p of x, then we can plug that into here. So what we basically have is the kinetic energy operator equals px squared over 2m, and we also know that px is equal to this value here. So if we plug that in, then we also have t equals I h bar d by dx all squared over 2m, and that equals, as I squared is the square root of minus 1 times the square root of minus 1, which equals minus 1, we end up with minus h bar squared d squared by dx squared all over 2m. And that's what the kinetic energy operator is. And that's another important thing that we need to memorize and keep. So I'm going to add that to my important boxes at the top. So the kinetic energy operator equals minus h bar squared d squared by dx squared all over 2m. And I'll get rid of this and put that in a box. Okay, and they're the important bits of information we need to know. Going back to the original Schrodinger equation, which is h psi equals E psi, we now know that this part is the same as this. So we found out what the kinetic energy operator yielded, which is this. So we can basically plug in this and this back into the Hamiltonian and get minus h bar squared d squared by dx squared divided by 2m plus, that's the kinetic energy operator, plus the potential energy operator, which is kx squared over 2, and all of this should equal E psi if it's all multiplied by psi. Okay, and that is the Schrodinger equation for the harmonic oscillator. And now to solve the Schrodinger equation for the harmonic oscillator, we need to find a trial wave function. And for the trial wave function, I'm going to be using the wave function. AE to the minus a alpha x squared. Okay, this is going to be my trial wave function, and we need to use this and plug it into here. Okay, so we need to find the derivative of the wave function. So the first derivative, d psi by dx, will equal just a normal derivative, minus 2 lambda this normal derivative, it equals minus 2 lambda x a e to the minus alpha x squared. And then we have to find the second derivative, which is d psi squared by dx squared. And to find that, we need to use the product rule. So u du by dx, v dv by dx. If we use u to equal this here, this part, so minus 2 alpha x, and the second part, v, to equal a e to minus alpha x squared, then we have du by dx, which will equal minus 2 alpha, and then dv by dx, which will just equal the same as this. So it's minus 2 alpha x a e to the minus alpha x squared. So we find out that it's u times dv by dx plus du by dx times v. So we find out that d squared lambda over dx squared equals, that would equal 4 alpha squared x squared and we also know that ae to the minus alpha x squared is psi. So if I just simplify things and just make it a psi here, and then I take away 2 alpha, and then this also equals psi, so I just put in psi, and that's the d squared by dx squared. And now I need to plug in this value back into here. So I'm left with minus h bar squared over 2m, and then I plug in that massive equation right at the bottom, which is 4 alpha squared x squared psi minus 2 alpha psi plus k x squared over 2 equals e. Psi. Okay, so we've got this now. And now, after we've got all this, we need to see if anything cancels down. And we see that there's the value of psi that cancels down, so we can just get rid of all the psi's. Okay, and also we know we have to realize that the energy is always a constant, therefore no value of x, which is part of here, can be equal to the energy, because obviously x is a variable and it can't be equal to a constant. So what we have to do is that we have to make the areas that have x equal to each other and the areas that don't have x equal to e. So basically, if we multiply this out, then we have minus h bar squared over 2m times by 4 alpha squared x squared minus is plus h bar squared over 2m times by 2 alpha plus kx squared over 2 equals e. And then we look for the bits that don't have x or x squared in, which is this here and e. So we have to conclude that h bar squared over 2m times by 2 alpha equals e. Obviously the 2's cancel, so we have h bar squared over m times by alpha equals e. Okay, and then the other bits are equal to 0. So we have, if I just rub out the other side of the board, so the other sides of this equation are equal to 0, so we have minus h bar squared over 2m times by 4 alpha squared x squared plus kx squared over 2 equals 0. And let's times everything by 2, so we've got minus h bar squared times by 4 alpha squared x squared over m plus kx squared equals 0. We want to find out what alpha is equal to, so let's times everything by m. Minus h bar squared times by 4 alpha squared x squared plus kmx squared equals 0. The x squareds cancel, so we're left with h bar squared times by 4 alpha squared equals km. If we divide by h bar squared times by 4, then we have alpha squared equals km over h bar squared times by 4, and then alpha is left with root km over h bar times by 2. And that's our value of alpha. And now we've got our value of alpha, and we've also got our equation here, which has an alpha in it, and we need to find out what the energy is. So we can plug in this value here into here. So to do that, we can just plug it in simply. Which will be h bar squared over m. Alpha is equal to km root km over 2h bar, and that's equal to E. It can simplify further because the h bars can cancel, so it's h bar over m equal times by km over 2, and that's equal to E. And now finally we know that the root m over m can cancel, so we're left with h bar over 2 times by k over m equals E, and that's our energy. And we know that it's a solution to the Schrodinger equation because all of this is a constant, and a function times by a function times by a wavelength, a function times by a wave function equals a constant times by a wave function, which is shown here, and yeah, that's the solution. And to elaborate on this further, we know that root k over m is equal to omega, so we can just end with E equals h bar over 2 omega. And that is a solution. Done. Whew. It's done. It's done.